your question.
For question 7.
All right, good. Questions number 7. Yes. All right.
I'm thinking worst case efficiency means it's a higher number, like it's a higher value, kind of like it's a higher value for a big O notation. Is that like, so something that's best case efficiency, which is B, that would be a less value. B is less than W, right?
Correct.
B less than W. Okay.
Correct.
That's just I just wanted to make sure because there's not like a number for it.
We have precise formula, right? Remember, our B equals 1.
Oh, okay.
Best case 1, right? Top root. So you compare with the root, binary tree root. You get it. That's best case.
Is best case always 1 for every situation?
Yes. For binary search, best case always 1. All right. B always 1. Worst case, we have formula, right? Okay. W equals 2 formulas. 1, you can write like this. Second one, you can write this. But here, the formula is not important. Okay? You just know it. We have these formulas. But the important thing, remember in class, I did one special example for average case. Here, our main concern is the average case, A. Do you remember in class, I did one average case computation in the notes for n equals 7, power of 2 minus 1. Because this one, relatively simple, so I draw a binary tree, to do the weighted average, we count. Do you still remember that? You can look at your notes. It's on your notes. After that, so here, the result, not that important. But after that example, do you remember I made some comments? The comments important. The comments is related to this question directly. The comments. In my comments, so let's recall, do you remember a little bit how close is the average case with the worst case? Did I say something?
Yeah, it's closer than 1.
Yeah, the difference is less than 1. Now, can you use that information to answer this question easily?
Yes.
Okay? Yeah. So that's the hint. You need to, go back. So basically, all questions designed based on notes. But some students send me email, ask me, couldn't find the background for your questions anywhere, in the textbook, notes. But actually, all come from the notes. Okay, all come from the notes. This one from the notes directly. Okay. So so now it's clear, right? Yeah, I hope it's clear. Yeah. And I wrote that formula, the difference, worst case minus average case, less than 1. I wrote that formula in the notes. Okay, all right. That's this one. Yeah. Next question. Do not have to follow order. John. Anyone?
We look at 22.
22. Yeah. All right. Yeah. B. Longest path. All right. So here, let me give you the general thinking way to solve this kind of questions. Actually, we use this strategy many times before. Right? So when you see the number of nodes here, n equals 1,236. It's a relatively large number. Yeah. So don't worry, because here, to solve this problem, the real number of this n is not that important. Okay? It's not that important. That means let us reduce this number significantly to a relatively small number. Then we can solve easily. Then after that, because after we solve it, we know what's going on. Everywhere details. Can we extend it to our target case, right? This big one. All right. Here, how about I choose n equals 9? Okay, a relatively small number. Okay, so now we can draw a heap. So let's draw one quickly with 9 nodes near complete binary tree. Here already 7, 2 more to go, right? So 2 more to go. Okay, all right. So here n equals 9. Longest path from root to the, you can see easily, right? Yeah. Because the starting point from root to a leaf, this is 1, this is the second one, right? And 3 more leaves, but not the longest, right? One shoulder.
Easy.
One shoulder, right?
Yeah.
So when we count, okay, we count. How do we count the length of a path? Number of edges. 1, 2, 3. That's you count the length of path. Number of edges. Okay? 3 edges longer than those 2 edge paths. Okay, 2 edge paths. Here, when I ask you longest path for this answer, your answer is 2. Okay? Answer is 2. But you need to summarize it. How do we get to it? The number of nodes at the bottom level, right? The number of nodes at the lowest level. Okay? The bottom tree. So how to calculate lowest level? All right, so here. Because if we ignore the lowest level, we look at all the nodes above that lowest level, the total number should be power of 2 minus 1, right? Yeah. So here, that's right. Power of 2 to the k minus 1. So that's the number of nodes above the lowest. But that number should be less than or equal to n, right? Yeah. Less than or equal to n. All right. Now, here, let's look at, because here our n equals 9. Right? Oh, sorry. Equals 9. What is the largest k so that 2 to the k minus 1 less than 9? Can you see that? Largest k, 3, right? So the largest such k, 2q minus 1 less than equal, that's the largest. So this number we should use because that's the number of nodes above the lowest level. So the answer should be 9 minus that power of 2 minus 1. 2. Okay? So we're calculating this way. After this simple example, now can you go back to the general case m, this time n equals 1,236. Same method. Power of 2 minus 1 less than or equal to 1,236. You can find that k easily, right? After that k, can you do the last step? calculation to get your answer. All right. Yeah. Next question.
23. I just want to clarify.
Yeah.
So like when 6 is our pivot,
Right.
and 10 is greater than 6, 4 is less than 6, so we swap 4 and 10. And then 5 is less than 6, so we swap 5 and 10. And then 9 is greater than 6. And then 2 is less than 6. How do we know that we should swap 2 and 10 instead of, say, 2 and 9? Like, does a computer know, like, okay, I need to do 10 this time or 9 this time? Do we have to explain that, or?
You don't need to explain, but we know why, isn't it? Because when you swap 2 and 10, 2 is adjacent to, those elements smaller than the pivot, right?
Yeah.
If you swap 2 and 9, not adjacent,
Yeah.
Yeah.
Uh-huh. Yeah, I know that's what it's supposed to do, but I don't have to like
You
explain
don't
more
need to
than
explain.
that.
Yeah.
Okay.
You just do it.
Sounds good.
But after you understand that the reason, don't tell me that. Just work on it.
Okay.
Okay? Give me the result.
Uh-huh.
I just check your final result. All right. Next question.
44.
40.
24.
24.
24. Yeah. I heard 44. So, yeah, 24. All right. Max heat indices 1 through n, smallest. So here, all right. Actually, it's pretty straightforward. Okay. Smallest possible index for a node with height 1. All right. It's pretty easy.
Is height 1 the bottom or the top?
Our definition, height.
Oh, so height would be the low. 1's the lowest.
Yes, come from bottom, okay? From 0 level. First, we need to understand the 0 level. The definition of zero height. What's the 0 height?
The leaves.
Leaves. All leaves, 0 height. Okay?
Leaves on the longest paths.
No. Don't get confused.
Okay.
Yes. Because, let me clarify. In class, I mentioned when we understand levels, height, there are 2 different ways. People can get confused. So here, let me clarify that confusion. All right. So let me, let me just draw like this. All right. Because when we count the levels, one way, so this is a binary tree. One way we count the levels, there is a definition, understanding about the binary tree levels. Binary tree levels, okay? So that is one way of understanding. That's the binary tree levels. That's one way to understand. Another way to understand levels, the heap levels. Heap levels. All right? Yeah. So we need to separate. Binary tree, because usually we say root, that's top level, right? Yeah. So then the next level, we come like this. If we come like this, then longest path. So you can see, there is one level for it, right? But another way we look at from the bottom, that's the heap levels. So when we talk about the heap levels, okay? Because the height of all the leaves equals 0. Height.
Okay.
Height, for leaves, L equals 0. Then, when you look at it in that way, these are the leaves, all right? You can see all leaves on the same level, height is 0 level, okay? All leaves, when you look at from the bottom, they are at the same level. Height is 0 level, all right? Yeah. So the next level higher, height 1 level. Okay? Height 1 level. So you should
Okay.
understand that. Okay? So, yeah. Different from the binary tree levels. So that is one. Yeah. First point. Do not get that confusion. Second, answer this question. You need to know the range. Range formula for nodes with height 1. Do you know that range formula for height 1? The formula, the range. Okay? Range, what is the lower bound? Lower bound for that range. Something plus 1, right? Something plus 1. Floor function n over 4 plus 1, right? Upper bound, the range formula. N over 2. This is the range formula, right? In our notes, do we have that formula? I wrote inequality. Remember, I know the inequality. But here I use the interval. So here I use closed interval. Okay? In general. So let me write the generals. Here it's the height 1 case. Let me write the general case here. The general case. Range formula. Closed interval n over 2 to the h plus 1. Floor function plus 1, comma, n over 2 to the interval, closing.
I just need to clarify, when you say closed interval, does that mean those values at the end are included or not?
Included.
Okay.
Open, not included.
Okay, yeah. I just
Open
forgot.
interval, not included. Closed interval, included. Okay? Open parenthesis, not included. Now, can you answer this question? The range is given, right? The range for what? Range for indices of the nodes, right? Yeah. When we talk about range for indices of the nodes. So now you can answer the question, right? The smallest, you find the smallest in the range, right? That's all you need.
And just a quick question, do we let the root node, so it looks like where the values correspond to the index number 2. Like, and for the root node, the one on top, is that assigned the value of 1?
1.
Okay.
1. Excluding 0. Okay? Forget about the 0.
So when something's a floor function, and this is kind of a dumb question, but if it's like a fraction, it just goes to 0, right, as a floor function?
Rounded it down.
Round it down to 0.
Rounded it down. Floor function. CV function, rounded up.
Yeah.
All right, yeah. Okay? Yeah. All right. Next question. Yeah, oh yeah. 21. Can we, yeah. I just said in the notes, we did one for order. Actually, remember, yeah, I don't remember if we,
Oh,
yeah. Did we do any similar question? Anybody? No? Never? Okay, never?
We did the 7-node example.
Yeah, 7 of, yeah, but not, yeah, all right, yeah. Okay, yeah. Let me do one. But let's do with slightly smaller number. How about that? Okay, so easier for us. All right, so here, how about we do n equals 12? Also even number. Okay. All right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, all right. Here. Let's run the binary search. Let's draw a binary tree corresponds to the binary search. All right. Here, remember, because we need to use the median. Remember, we define left median, right median, right? Yeah. When there are even number of elements, when we talk about median, there are two medians, left median and right median. But by default, we take the left median. But I noticed, based on communication with a few students, some students, when they search the web, they wrote the median. They use some formula, commonly used from web search. They use, just index of the first element, last element, take the average. They use that as the median formula. Right? If they do that, that's the right median. Okay? That's the right median. For example, but actually here, because when you look at the index, you start from 0 through 11. Okay? Yeah. So you use 0 plus 11 over 2 floor function. What do you get? You get 5, right? 5, index 5. Oh, yeah, that's left median. Okay, yeah. That's index 5 corresponds our number 6 here. That's fine. That's fine. Yeah. So that's the same thing. Yeah. So floor function. If you use ceiling function, that's the right median. Okay. All right. All right. So here, let us, just this number. Yeah. All right. Let me draw binary tree. This is the median, all right? This is the median. That means the first comparison is here. The first comparison is here, okay? Let me put 1 here, okay? That's the root, 1. Then left half, yeah, the second comparison, here. All right? Second comparison, how many? 6 left median, second here, okay? Second comparison here, all right. So first comparison, yeah. Let me just put up, the node, I put this node number, 6. 6 and 3, node number 3 here, right? Yeah. 3, because left median 1, then 2. All right. 3 moving to the right. All right. Yeah. 4 and 5. 4, 5. All right. This way. Then right side 9. Right. Node 9 here. Node 9, 7 and 8. 7, 8. 11, 10, 12. Yeah, all right, so that's the binary tree we, draw corresponding to the binary search for this question. Then, now I take some, range, selected range, similar to elements selected in some range. Here, how about I select this range? Okay, I only consider elements in this range. Out of it, remove it. Okay, do not consider it. Then, when we look at the elements in this range, 6 is here. All right, so 6 here. Yeah, so 1, 2, 3, 4. Let's cross out because we don't need it. 1, 2, 3, 4. Okay, cross out 11 and 12. Cross out. Okay, we don't count it. That only we count the remaining nodes, existing nodes. 6, 1 comparison, right? 9 and 3, 2 comparison. Okay, this level 7, 3 comparison. The bottom level 5, 8, 10, 4 comparisons. Right? Now let's write weighted average. Weighted average. One comparison, only one node. So 1 times 1. 2 comparison, 2 nodes. 2 times 2. 3 comparison, 1 node. 3 times 1. 4 comparisons, 3 nodes. 4 times 3. Total number of nodes, 6, right? Yeah, because you count the number of elements in the range. There are 6 elements. So the denominator 6. The numerator, you use that way. Okay? Number of comparisons, how many nodes? Multiply together. Next term, number of comparisons, count number of nodes, multiply together. For this question, you just work on your scratch paper. You may need a little more space. Scratch paper, 26 nodes. Yeah. The range, you draw the binary tree carefully. Okay, carefully. Then the range, in the range, there you come. How about that? Okay, how about that? Yeah. If you count carefully, the method is correct. You may get a mistake. If any, the method is correct, exactly this one, but in your calculation slightly wrong, I only take 1 point off. Okay? But make sure, if it's correct, make sure it's correct. Do not lose that 1 point.
How much should I be explaining the binary tree? Or like,
No explanation, just draw it.
just draw it? Okay.
No explanation, just draw it.
And we should always use the floor of min plus max divided by 2 for like each each median, I guess. Yeah.
Each median, use that left median. Left median. But if some students use the right median, I give you full credit. Okay, just one of the 2 options. Left median, because our assumption is the left median. But if you use the right median, it's not wrong. It's not wrong. Okay? But I hope take the left median if you do not have any, any special consideration, just take the left median. Next question. Before you tell me, let me make comments on 2 questions. Let me make comments on 2 questions. This is 1. Number 16 is 1. All right. Number 11 is 1. Yeah. These 2, let me put together. These 2, they have similar properties. So I make comments together. number 11. So here, there is a statement. You need to tell me if this statement is correct. Given any positive integer n, can we say that one can always represent phi to the n in the form of a phi plus b, where a and b are certain integers? Certain integers. Yeah. So, true or false? Correct? Yes or no? To see that, yeah, because here you need to consider all possible integer n. But nobody can test it for all possible integer n, right? Impossible. So, but in class we learn a special method. So these two questions, number 11 and the number 16, both these questions are designed to understand that particular method. So here I'd like you to do practice mathematical induction. Here you need to use the mathematical induction thinking, based thinking, to understand, to see this question. So you feel okay, right? Mathematical induction. Yeah. So let me put here. Induction. Okay. To view the answer. And that definitely plus the properties of golden ratio phi. Okay? So these two things, we can get an answer. You can get an answer. All right? Yeah. All right. For number 16, it is harder than this one. Yeah. Number 16, it is harder than number 11. Both use mathematical induction plus the properties of golden ratio, but here there is one more. There is one more thing you need to use. Because if those two, there is another critical step you need to know. That is, you need to know this. When you multiply these two formulas together, what would you get? Right? Yeah. Here, you get this. Formula. Okay? But can you see something useful here? All right? Yeah. Here, let me use a notation. Yeah, because this formula, if I write, whole thing, I need to write long formula. How about here I use a sub 2n to represent it. So then I can write it shorter, right? I can write it shorter. All right. Then this formula I can write a sub 2n times a 2 equals this side a sub 2n plus 2 plus a sub 2n minus 2, right? much shorter. Right. Then we write, because our goal when we use the mathematical induction, so here I assume you know the details of mathematical induction, okay? Yeah. Otherwise, it's hard for you to understand. 2n plus 2 equals 2n times 2 minus. All right? Yeah. When you see this formula, this is the formula that we need to use to get a conclusion for the mathematical induction. For the conclusion. But you need to know those 3 steps, all right? Yeah, why we can get a conclusion from this formula. You need to know that, okay? Yeah, because based on our assumption, in mathematical induction, we need to make an assumption, right? Yeah. The assumption is the formula like this should be a positive integer when the exponent in the range, in certain range, okay? Certain range, yeah? All right, so here, 2n in the range, 2n minus 1, minus 2, 2n minus 2 in the range, right? So in the range, then positive integer. In the range, positive integer, okay? Yeah. Take the difference is integer, you may not see positive. You can see their integer difference must be integer. Can you see the original one must be positive, right? Any A something, A sub something must be positive, right? So if it's integer, it must be positive. Okay? So can you make induction conclusion based on the formula here? But you need to go through all the details for mathematical induction. So these 2 give you a chance to practice understanding of mathematical induction. It's very important. No. In discrete math, you learn the first time you learn it. So this class you learn it the second time, mathematical induction. All right? Yeah. Yeah. That's these 2 questions. Next one. Next one. No more, right? James?
Yeah, we were going to ask about 19. We were going to ask about 19.
Oh yeah. All right, yeah. So here I need to show you how to work on these questions. Yeah. So let me work on one with n equals 12. All right. Larger than this one. Then you do the same way on 10. Worst case, right? First, let's get the worst case formula. Worst case formula. When we merge n and n, the worst case, the formula is n plus n minus 1, right? Yeah. Because here we split first. We split our array into many subarrays. Then we merge two adjacent subarrays. At the end, we get a whole array. So that's our, standard merge sort procedure. We need to go through all this details. But when we do that, here I need to use some notations, simple notations. So here, look at this. This means we merge two ordered arrays with first one m elements, second one n elements. Okay, yeah. So here, so the worst case formula. But the merge result, I want to use a short notation to represent the merge result. Yeah. So then, with that short notation, so I can apply it everywhere when we do the merge for this question. So my short notation is, all right, after we merge, we get this. We need this many comparisons, but the number of elements after the merge, that's this one. So the first component gives us number of comparisons. Okay. The second component, that's the first one. The second component gives us number of elements. In the result array. Okay? Yeah. So that's our notation. All right? Yeah. So we use this notation. Now let us run the merge sort. Okay. All right. First split, okay, two subarrays, 6 plus 6. Set, so that's the first split. First split. Okay. Second round splits. Okay. Second round splits. Okay. Here. Second round splits. Okay? All right. Then, third round splits. Third round splits. Okay? Okay? All right, third round splits. Okay, then you may do the last round, fourth round split. Okay, fourth round, last round split. All right. Yeah. So after all the split, let's do the merge. When we do the merge, we just reverse our order split. Reverse the order. Okay? Let's do the last round merge. Yeah. Corresponding to the last round, the merge. Our first round, but corresponding to the last round split. Okay? All right. Merge 1 and 1. Yeah, so one element, 1 and 1. So these two, the result, merge result. if we use our notation, how many comparisons? One comparison, right? Yeah. One comparison. So yeah, this one, in my notation, I need to use a special one because I don't want to confuse with other notation. Vertical bar, okay? I draw vertical bar. Okay, vertical bar, all right? So here, number of comparisons, one, so I put one here, vertical bar. Number of elements for the result array, 2. So that's my merge. 1 bar 2. Okay? You know the meaning? Yeah. Because we need to use this information every round. Okay. Every round. All right, here. 1 bar 2. Here also. Okay, all right. Then merge corresponding to round 3, right? Yeah. But this time we need to use 2 and 1 element. 2 and 1 element. Okay? 2 and 1, number comparisons. 2 plus 1, 3. 3 minus 1, 2. Okay? So the merge result is 2. The number of elements, 2 plus 1, 3. Okay? All right. So reverse, 2 bar, vertical bar 3. All right? This round, 2 vertical bar 3.
I'm sorry, 2 stands for
Number of comparisons. 2 stands for number of comparisons here. Okay? 3 number of elements. So now we reverse round 3. Okay? That round 3. All right. Reverse round 2. Round 2. Merge these two. Okay? But this time we need to use element 3 and 3. Okay? 3 and 3. 3 plus 3 is 6. 6 minus 1, 5. Okay? So this merge, I need to use, let me use space here. Okay? So 3 plus 3 minus 1, 5. Number of elements, 6. Okay? So these merge, we get 3 plus 3 minus 1, 5. Number of elements, 6. Okay? Now, we get a last.
and this is strictly for worst case, right?
Yeah, worst case. Best case, we can also use this way. Just switch the formula. The formula would be different. Minimum of n and n. Only change the formula. To replace this formula for the best case by minimum. Yeah, minimum. Comma n. Okay? This is for the best case. All right. The last round, because now you know the last round merge. Final round merge. 6 plus 3 minus 1, 11. Vertical bar 12. So you merge all of them. Then the last step, accumulation. All the comparison, you need to accumulate them. Right? Accumulate. All right. So this round, accumulate 4 ones. So this round, now total number comparison, subtotal. Subtotal comparison, you get 4. Okay? This is subtotal. 4. This round. Okay? This round, subtotal comparison for 2. 4 times, right? So this round, subtotal, so I need space, 8. 8 subtotal, okay? Sub, let me just write sub, all right? 8 sub. Then this round, 5 and 5, right? Yeah. This one, 5 and 5, 10 sub, right? Yeah, because the last round, 11 sub. The last one, 11 subtotal. Okay? Then we get total. Now we calculate total. The first sub, that's 4. Second sub, 8. Third one, 10. The last one, 11. How many? 33, right? 33. This one. Try to understand this way. Okay. So you will have the video, and I uploaded this, this file, this PDF file. Okay. So you can use it. Deadline tomorrow, Wednesday, plus 1 grace period. So hopefully you can, this time you have enough time.
I had one clarifying question about 21 again. If the notes are still there.
Yeah, still there.
So like, 5 is in the range, but it's downstream of 4. Like the algorithm would need to make that comparison to get to 5. So should we count that or not count 4?
5 in the range. Yeah, we should count.
We should count 4.
Okay. Oh, good question. Yeah. Because we cross out 4, right? So here, I try to understand your understanding. Because we cross out 4, so we cannot get 5. Is that?
Yeah, that's what
Yeah. So here, we view this one, we use the probability here, okay? Probability. So all these nodes in the range, we look at them with the probability, okay? So for the nodes out of the range, we set probability 0. How about that?
Okay.
Yeah. But the nodes exist, just the probability is 0.
I see. Okay.
Yeah. So we need to go through 4. Yeah. But in our weighted average, that one corresponds to weight 0. Okay. So we don't have 0. Okay. Yeah. But for the integrity, yeah, because the whole tree, you cannot break it. Okay? The whole tree, you have to view it as an integral object.
Yeah, and I guess that comparison is still taken into account because you're weighting 5 at 4, like it's still happening, it's just not.
You need to go through it.
Okay.
Yeah.
That makes sense.
Yeah, but 4, good. Yeah. So, to get a better understanding.
I have a question on, it was problem 5, I think.
Problem 5. Yeah.
I just want to make sure it's not a typo. So C is saying R is greater than or equal to 1, but B says equal to 1. So if I select C, that also means B, right? Like, because C includes B.
Always correct. Okay. So because in my wording here, I said always correct. Yeah. Although C included 1, but can you say C always correct?
If B is always correct, then C is always correct too. Because 1 is greater than or equal to 1.
How about if R equals 0 sometimes?
Well, then both B and C are wrong. What I'm wondering is just like, I can select answer
Right.
C, and that seems like it always
Right.
includes answer B.
Yeah. So just make sure always correct. That's what we need.
Okay.
Then B and C wrong, then they're gone. Then they're gone. Okay? If you find a situation that R equals 0, then B and C gone. Because they cannot be always always correct, right? Look at
I
that.
mean, okay, now staying on this question, it seems like none of them are always correct because sometimes R is one, say, if there's two nodes, then it's a root, and one node, the root has no right child, so then the root, that is one node that has no right child node. But what if there's just one node overall? What if there's just one root node? Then there's no eternal nodes, right? Or if there's just what's the case for when n equals 1? That would be R equals, I'm thinking R equals
One
0.
right child. Do we have a situation some node has one right child? Oh, number of
If it has the right child, it has to have the left
right
child.
Okay.
So another
Yeah, you're right. Yeah. Yeah, good question. Good question. Good question. Yeah, actually, yeah. What I want to ask, yes, actually, so yeah, in my mind, I want to ask, yes, yeah. So this question has a problem. What I'd like to have is for those nodes, this R should be those nodes who have only left child, no right child.
correct.
Yeah, I want to say that.
Mm-hmm.
Yeah, but I say here, I say intern have do not. Oh, yeah, that's the same thing, right?
Mm-hmm.
Those nodes who have left child but no right child. Internal, it must have some child nodes, right? Internal. Yeah. Internal without right child, it can only have left child. Yeah. Now your question, you said none of them correct. So can you give me two such nodes? Yeah, because if you want to say A is wrong, if you need to give me at least two, R equals 2, then you can say A is wrong, right?
Mm-hmm.
Do you have a situation you can give me two nodes in that heap? That those two nodes, they only have left child, they do not have right child.
I guess this is for like an unsorted heap, so we fill it out basically from
Max heap.
Yeah,
That's
max.
actually max heap. Yeah, because, do I say? Yeah. Yeah, max heap or not, actually not important because our heap must be near complete binary tree. If it is a near complete binary tree, then we have this problem.
Okay, so yeah, I see actually right. Yeah, now I see. Now I see.
So I'm not wrong. Yeah. I got confused. Yeah.
I did too.
Yeah. It's not wrong. All right. Yeah. So we only have 5 minutes. So last question you can ask.
19.
Yeah,
19.
19. We finished 19, right?
You did 18.
18. Oh, we did 18. We did 18. Oh, okay. Oh, James, you asked me 19 before, right?
Yeah.
Oh, yeah. Because 80 in my mind. Some other students sent me email, ask me about 18. So I did it. All right. So now we do 19. Yeah. 19. First, we do the best case or worst case. Here, best case. Best case, but here we have 3 ordered array. These 3 ordered array, let's assume the number of elements in them, A, B, C. How about that? Okay, A, B, C. Number of elements. Yeah, but here, when we need to find the best solution, we want to, because there are several possible solutions. We need to compare which one gives us the best. So the first one, right? The first method, okay? We merge A, B first. A, B first. Okay? AB first. AB, so we get A plus B. Number of elements in the merged array, right? Okay. But after that, you need to do another merge, right? So you need to do A plus B and C, another merge. Okay, so this is the first method. Now, can you do the second method? We merge A and C first to get A plus C elements. Then, but we need to do another merge, A plus C and with B. Okay, the second possible solution. The third, B and C merge them first. And we get a B plus C number of elements. But we need to do another merge, B plus C and A, to get our third solution. Among the third, you need to pick the ones, smallest number of comparison. Okay? Best solution. That's how you do it.
What about for the worst case, like in the 20th question?
Worst case, right? Worst case, you do the same way. Just use different formula. Best case, you use the best case one. Okay? The best case, this one, when you do the merge, you use the best case formula. Worst case, use the worst case formula. But after you finish these two questions, you want to see one of them, the greedy algorithm will give you the correct answer. Greedy algorithm. About both. Yeah. We talked about greedy algorithm before, right? Yeah. So the greedy algorithm works for one of the two cases. Here I do not tell you which one. Okay? So you need to do experiments by yourself. So then your conclusion. For your conclusion, you know greedy algorithm. First, I hope you know what's the meaning of greedy algorithm, right? James, do you know here how do we apply the greedy algorithm? Greedy.
Yeah,
Greedy algorithm.
it's been a little bit.
So here, let me clarify it. Okay, clarify it. For this question, greedy algorithm. Right here. Yeah, because for those online students. All right. Greedy algorithm. We need to use greedy strategy when we merge two arrays. Yeah, here. These three arrays. There were three numbers here. But when we merge, we treat the smaller the array size, we use fewer number of comparisons. That's the greedy. It's greedy strategy. So we select two shortest array to merge first. Okay? Two shortest array to merge first. Then next. This is greedy strategy. Okay? Yeah. If this approach gives us the best solution, then our conclusion is the greedy strategy works for this method. But one of the two cases, this greedy strategy does not work. Yeah, one of the two, it does not work. So this tells you the greedy strategy will not be always work. It won't be, it won't hold all the time. Okay? Yeah. So you should be very careful. When you apply greedy strategy, you should be very careful. Sometimes it doesn't work. Okay? You should be very careful. All right? Okay, that's it. Yeah. So I will upload, so you can use it to, complete your homework.
Sir, what is the